All right. So, I don't know whether someone wanted to ask it, but I'll just go straight into answering that first question that's on that first slide there, talking about costs associated with live work. From Powerlink's point of view, certainly with my side of things at Powerlink, a couple of areas that we look at, and one of them is disconnector maintenance. And with our disconnector maintenance, our budgets are actually set the same for live substation work as it is for de-energised work. And this works out because with the layouts of our switch yards at Powerlink, the majority of our disconnectors that are maintained live are done in such a way that it's not necessary to shunt. And in this scenario, it's in fact quite quicker and cheaper to do it live. However, this is then offset against there is a number of disconnectors in our system where we do actually have to shunt it. And when we go to do this, these are more expensive, but there's a lot less of them. And basically, it ends up evening itself out across our population of the disconnectors that we maintain to effectively being the same costs when it comes to doing disconnector maintenance. Putting disconnector maintenance aside, for various corrective maintenance or project work that we do, the costs associated with carrying out this work live are considered basically in a whole holistic view for each of the individual jobs that we partake. The difference in costs for these between the live and the de-energised can vary considerably depending on the complexity of the work, and that versus the cost of the actual outage, should they take the outage. So it's hard to answer it unless you look at each of them from an individual basis. Some jobs are complex and more expensive, and they may not even have any real outage costs, and yet they're still done live, and that ensures our system security, and that really comes down to a business decision. And then you have some jobs, in some examples, that aren't necessarily complex, but would need generation support if you were to do them de-energised. And there's been some cases where we've carried out work where we've saved in excess of $100,000 a day by doing it live, and that quickly adds up to some significant savings. So there's areas that it's more expensive and there's areas that it's less expensive, and it's really looked at it from a case-by-case basis. That's the best way I can really answer that particular question.
Yeah, thank you, Brad. I think you definitely answered that well. Do you want to move on to the next one?
Yep. All right, so connecting new bus bars onto existing live bus. And basically asked there for a bit of a step-by-step description on how we go about doing that. So to start off with, the new bus bar is constructed, leaving a gap between obviously it and, as in the new bar and the existing bar that's in place. Any plant that's connected to the new bus, what we do is we open up the bus isolators, and that way the amount of plant that we're actually connecting initially is minimised as much as possible. And the reason for this is we need to make calculations to ascertain the actual capacitance of what it is we're connecting. And depending on that amount of capacitance, this will determine what actual procedure we use and whether we need to use a particular device for making that initial connection. So we have a couple of devices that we use, and they all have a capability, I guess you could say. And so before we actually make that initial connection, we'll obviously make the necessary checks on the bus bar to make sure that it is ready to be commissioned. So, and basically actually doing that initial connection, I should say, just to get voltage on the new bus. The actual physical final connection can be done a couple of ways. You can use bridges to connect between the old and new, or you can use directly connecting aluminium bar. So if you're using bridges, it's simply a case of bolting them down onto the palms of the bus bar. If the existing bar doesn't have palms there to bolt your bridges onto. It's a case of we can crimp on connections that have built-in palms to bolt onto. If you're not using bridges, you can directly use a length of busbar, and that's lifted into place. You can either lift it in place using hot sticks, you can lift it in place using cranes with insulating sticks from the crane hook, or we can use various telehandlers, again with insulating poles in order to hold on to the new bar, and basically lifting it into position, and then we actually use crimps, inline crimps to crimp the bar off. So hopefully that answers that in a step-by-step way of physically connecting the bar. Later on in the Q&A sessions, we actually have a series of photos when we're answering another question, and in those photos we'll actually show you some examples of connecting in the bus bar.
Yeah, I think that would be great, Brad.
All right, I might,
I'll move on to the next one.
I didn't quite get what that was, so we might move straight on to the next question.
Yeah, sounds good.
Yeah, sorry, did someone ask a question then?
No, just commenting that. Sounds good to move on to the next question.
Okay, sure. All right, looking at preparation, and actually on the slide there, we've just put a few little bits and pieces on there about what is generally included in the preparation stage before we actually get out to site to carry out the work. So first up, the guys actually go out to site and do a measure and scope, and so they're looking at taking phase-to-earth or phase-to-phase measurements. They do an insulator percussion test and some measurements on the insulator, so that's to get an idea of the actual insulator withstand that's in place, and they do some general layout measurements. So when they're doing the measurements in that stage there, they're using hot sticks with a particular measuring stick that's got coloured increments on the stick, and allows the guys to actually take physical in situ measurements while it's still live. They then come back to the office and start the actual job preparation phase. And so from those measurements that they've taken in the field, they do various calculations on making sure they have adequate insulation withstand. Depending on what job they're doing, they may need to do calculations for changing state. So if we're doing a connection or a disconnection, we need to do various calculations associated with changing voltage states. If we're putting in place shunts, we need to do various calculations on changing transit states. They put together a series of drawings showing each stage of the work, making sure that there's adequate clearance distances, and they'll vary depending on what the actual work is that's being taken place. Are you moving operators between phases or moving bits of plant or equipment? That's all got to be included there in the drawings to make sure you've got that adequate distances. And as well as that, there's the step-by-step procedure that goes in hand with those drawings, stepping out how the job's going to get done. These are all checked and approved by an engineer. So I should say that the measure and scope and the job preparation are done by the field workers, the team leader in charge of the job. Excuse me. So he goes through and does all that preparation, and then after that it's then checked by the engineer. You'll also note there at the end that on a monthly basis at Powerlink here that the team get together and go over job preparations that have been completed or jobs that have been completed through the month, seeing if there were any opportunities for continuous improvement. I hope we have a technical failure. Oh, we just had a computer crash. Would you believe it? It's restarting.
We can still hear you, Brad, but your video.
All right, I might get you to release that while I keep talking there. Sure. So So I'll just continue answering the question on the phone here while my friend gets this computer going. Yeah, so we do a meeting once a month, basically to close that loop and to take any learnings forward. So there's a question there from someone talking about the idea that the live substation work might be considered more risky than dead substation work. In response to that, the risk associated with high voltage are very carefully managed by the team and controlled. And it's the focus on that safety and the careful preparations that are carried out prior to the work starting that makes live work, in our eyes, in fact, less risky than dead substation work, purely from that actual focus that the guys have and the preparations required. So it's a perception, I guess, and that's the best I can comment on that.
Thanks for that.
Next question there about how Powerlinks have adopted the work or the live substation techniques from RTE. And I had a slide. I didn't put that slide on there, that's okay. Basically, how long did it take? Basically about a year and a half from when we looked at doing a feasibility study into taking on live work to the point where RTE put forward a proposal and that got accepted, and we actually started our first training of operators. It took about a year and a half to get that up and running. As for were we able to use RTE's approach directly, or whether things needed to be adapted, because of the way live work is carried out, it's a methodology that's adopted. So when we actually looked at taking on live work, we looked at a number of options of how other utilities around the world have adopted the different techniques. The method from the French was a very flexible method that can be easily adapted to what it is you want to do. It's not stringent, specific procedures on how to do things. It's a methodology and a set of rules and tools that are applied to individual tasks. So to answer the question is, yeah, we were able to directly use their methodology without having to adapt it. It's a simple matter of converting actual clearance distances to the voltages that we use on our network compared to the voltages that they use on their network, and got straight into the swing of things.
Excellent. Thanks, Brad.
And I believe this is the last question that's been put forward, talking about the complexity of live substation work. And asking about what types of work can be done live, and what I've done is following on from this slide, I've got a series of photos of some of the works that we have done. It's really difficult to put a finite list on what can be done live. We have times where people come to us with, can you do this? And it might be something we've never done before, and we simply go away and look at working out a solution. We often say that you're only limited by your imagination as to what you can do. However, it's always going to depend on having adequate clearance distances. So providing there's enough room, it's limitless as to what we can actually do. There are some, I shouldn't say limitless, there are some limitations. Things like power transformers, connecting power transformers. We don't work on those. We have limits as to what we can connect up with our different devices from a capacitance point of view. And one other thing that we don't do here at Powerlink, it can be done, but we have chosen not to go down the path, and that's actually welding live. We have I guess an issue with do we train experienced live substation operators to being welders, or do we train welders to be live substation operators? And it just gets a little bit too complicated, even though it can be done. It's a bit dicey due to the difficulties in welding. So what we choose to do is actually do crimping. Whenever we're doing joins to busbar, we actually use crimps. And you'll see some photos of these. So we might just move through a series of photo slides to give you a bit of an idea of some of the things that we do. So we talked before about doing disconnector maintenance, and one of the principal things that we do with disconnector maintenance is actually monitoring their condition. So this particular device here is called the name stick, so that's actually measuring the resistance across various joints. And I'm going to flick through these fairly quickly because there's quite a lot of them. To simple cleaning, scouring pads on sticks. This particular photo here shows a 275 kV isolator that's been shunted out. The isolator is open, and the guy's simply cleaning contacts. And in this particular case, they're using a battery-operated device to do that cleaning. So anything that you can attach a battery to can be used live. Here's some more examples of, these are a 132 kV disconnector. You can see the 3 phases there shunted. And the next slide shows that disconnector with that's now been opened after it's been shunted, so again, can be maintained. And that's just a bigger version. And you can see there that we use aluminium scaffolding to actually hold our hot sticks in place. Or in this particular case, that's our little telehandler. We've set up a jig where we can hold sticks in place off the end of a telehandler. So that's a smaller isolator, and we can do all 3 phases in one hit and quite quickly. I know there's lots of things happening there, lots of bits of bar and droppers and stuff like that, but that's basically 3 phases have been shunted out in order to open up that disconnector and maintain it. Looking at corrective work, so in this particular photo here is where we've actually replaced a disconnector arm. You can see the nice shiny new one compared to the older one in the foreground. So when things, while we can repair things in situ, if you want to do significant repairs or refurbishment, it's easy to actually take the components out and replace them. That's just a similar shot of the same work. Here's a different disconnector. So again, pulling arms out, replacing arms are problems with high resistance joints. Again, if you look closely on that particular photo, there's a shunt around the phase that's been changed over. That's just a close-up view. A little bit harder to see in this particular case where we've lifted the whole insulator column and arms down using what you see there is a big hot stick, a boom. Effectively becomes a little crane for lifting items down. So in that particular case there wasn't enough room to get operators up there bare hand between phases, so we simply had to work hot stick and bring the equipment down. Even do a bit of painting. Painting some line traps. So here's a bit of substation augmentation. So this is where we've had to go through and replace all the disconnectors in the whole switch yard to be uprated, basically. And where they were connected directly onto the bus, we've had to disconnect and remove sections of bus in order to be able to replace the disconnectors. So there you can see lifting a section of bus out where the remaining section's actually been held up by an A-frame of hot sticks. Here's a close-up. And before we start cutting busbar, we like to drill a hole in it first just to make sure it's not going to be full of water. There's nothing worse than cutting through a bar and having water going everywhere while you're trying to do live work. So there's guys just drilling to verify there's no water inside the bar. It gives you a bit of a shot also of the sticks that are being used to hold up what's being left in situ. You'll also notice on those hot sticks there some black rubber sheds. So whenever hot sticks are left in place overnight, you need to set them up with sheds as part of our procedures. Same job, that's just one of our operators climbing to phase. And another shot of actually lifting out that bar and bipod. You can see in the background the other two phases being held up by those hot sticks in an A-frames sort of situation. And that's how we actually left it. So that's it, ready to go to pull that disconnector on the left-hand side down and be replaced. This particular substation has a large number of generators hanging off that bar, and it's near on impossible to get an outage on that bus bar. When we first started doing that sort of augmentation, our bus connections were a bolted connection, so that's the old bolted connection we used to use. We no longer use that, we now do crimps, and the next couple of photos will show actually utilising crimps. So this particular shot's just of an operator climbing to phase, and this is us doing some actual bus crimping. So they're the sorts of joins we now use when joining bus bar when we do it live. That shot there shows the completed crimp in the foreground, and the guys in the background just changing over those old bolted joints to the new crimps. Moving droppers. A part of our work, sometimes we have to move droppers. This is quite a tall one off our overhead strung bus. So you can see we use ropes as well as sticks for manoeuvring our gear around. Here you can see they're dropping those bridges down. Our tower does have a limit to its height. So one other option is to use our what we call a hook ladder. In this particular case, the tower is just a couple of metres too short to get up to make those connections. We've also used that same device here in this particular case, installing spacers on conductors. So that's the operator starts from ground level and is hoisted up to phase. Then when he gets to phase, he can move along the conductors. You'll see there, hanging underneath him is our measuring sticks. So obviously we're just checking and verifying distances as we go. Another shot of disconnecting droppers. Basically we're disconnecting a bay in this particular case. So the droppers connecting the bay are lowered down to disconnect the bay. And disconnecting circuit breakers, this particular type of circuit breaker, a PAS unit that we have at Powerlink. So again, you can see the conductors are maintained by those hot sticks that are mounted on the scaffolding and moved out of the way in order to so that we can change over that circuit breaker that has an issue. There you go, there's all three phases held back out of the way. And if you actually look closely at those three phases, go through those line traps and straight up and out on the feeder. So that's keeping that feeder in service, fed from the other side basically. Here's another way of just maintaining droppers, tying droppers back onto the ones on the other side there. And some more work, disconnecting circuit breakers. So with a lot of it sometimes we can get one feeder out off the bus, and so while we can take one feeder out, they don't want to drop the bus off and drop 5 or 6 or more feeders off the bus bar. So by keeping the bus in and dropping one feeder out at a time, they can work on whatever the problem is. It's just the drop has been removed. We spoke before about connecting bus bars. So this is one of the bus bar jobs where we've actually inserted the bar in. So the new bus bar is on the right-hand side of the photo. The existing old bus bar is on the left-hand side of the photo. You can see on that particular phase, first we had to go up and cut the old spheres that used to be on the end of the bar off. We're using a crane in this particular case, so we're just lifting down in to position the bar, hanging off that hook a series of insulated hot sticks that insulate between the crane and the actual bar that's been inserted into position. And next shot here, I spoke before about connection or disconnection devices depending on your capacitance. So in this particular case we've had to use a small device. Well, sometimes we can just simply make the connection directly. Sometimes we need to use this small device called the snail. That's that blue drum on the right-hand side and the receiver on the left-hand side, and you'll see a thin wire between the two. It's basically a coil-sprung wire that's been pulled across to make the actual connection. And here's that same device being used again to connect up a new CVT. You'll see that blue drum on the left-hand side, the receiver on the right-hand side, and that wire hasn't yet been pulled across. It gets pulled across using an insulating string. So if you've got really good eyes, you can see the insulating string coming off the receiver that's up on the bar. So the operators can be at a distance away and pull that connection across. There it is, being pulled. It's about a third of the way across between the VT and the bus bar. And once that initial connection's been made, then that dropper that's on the top, or the bridge that's on top of the CVT, can be moved over and the final connection bolted together. Here's a job where we've been pulling line traps out of place. So as we install fibre optic communication networks on our system, the old power line carriers and line traps become redundant. So instead of turning the feeder off to pull them out, we've bypassed these line traps and pulled them out. You need to be very careful, however, working with line traps because there's a voltage difference across the line trap. It can be quite spectacular. So what we do is, from a distance, we actually short out that line trap before we start doing anything on it. And that's what that operator there is doing. He's actually placing a shunt on the bottom side of the line trap. He'll then get moved away, and using hot sticks will actually make the connection to short out that line trap. There it is. Slightly blurry photo, but yeah, making that connection, we've actually put in place a little lug there because we know that we're going to get some burning when we make that connection to short out that line trap. This is just a slide that was in part of this particular presentation. So this particular isolator, that's what happened to it. There was a fault on a particular isolator, and our job was to shunt out, bridge out the whole, effectively a bay there, so that contractors come in and replace the isolator. So if you look, you'll see two phases already bridged out, third phase in the process of being bridged out. That's how he walked away from it after the first day. So 3 phases bypassed. That line isolator that's underneath them had that big melted part on it that you saw before. So that isolator was replaced, and then along we come and connect up the new disconnector. Being very careful the whole time current's flowing, so when you start messing around with various connections, you need to make sure that we're not breaking current paths. So as you can imagine, here's bits of shunts in different states of replacing that that bridge. There Here's the new bridge coming straight down, the old one that's about to be disconnected. Changing components over, like faulty surge diverters. We manufactured a specific grab that we can use off our telehandler for actually grabbing things down low, and changing various components over, like for example this surge diverter. Surge diverter carried out, new one brought into position and connected up. There you go, there's a bit of a taste of some of the work that we do.
Oh, great. Thanks a lot for that, Brad. That was some really interesting photos. Definitely gave me a perspective I hadn't even thought about before. We have a few questions that people have asked in the chat throughout the talk, if you're happy to answer some of them.
Yep.
Cool. First question we had, you actually already answered. We have two from Jack, showing up as Luke Arnold. His first question was, is there a requirement of limiting the load on the line or the bus when it's connected live? And he had another question about EMF exposure and if there's any, I guess, rules or regulations around that.
Okay, so the first question there about load. So when we're making a connection or a disconnection, we don't have load. That's what I talked about when we're connecting a new bus bar. We make sure all the disconnectors off that new bar are actually open, because basically we look at the capacitance when we're making a new connection or disconnecting something. Loads looked at when we're shunting things. So if we have a line isolator that has a problem on it, we need to look at the load on that line as to what size shunts we use when we're bridging out whatever the problem is. But when we're making connections or disconnections, there needs to be no load. So I hope that answers that particular question. With regards to EMF exposure, there are Panzer guidelines with regards to EMF exposure. When we first started doing live work, we started monitoring our EMF exposure of our operators, and when we started comparing that to these guidelines, the results were insignificant, due to the fact that with our high voltage, a lot of the EMF radiation is dependent on current, and with our high voltage, our currents that we have on our system are quite low. And so you end up having a lot higher EMF radiation from low voltage 11 kV or 33 kV mains compared to when you're up on the 132 or 275 kV. So while we looked at taking those measurements for a couple of years, we actually stopped taking them because the results were so low and we were putting a lot of energy into something that was, in our eyes, quite insignificant. Some new things that have come out with our discussion with the French is they put limitations on how close an operator's face can come to lines of higher currents. Although the studies that they've done have shown no lasting effects on the body, they've found that with very high currents that the operator's vision can be impaired. So they simply put a limitation on lines with very high currents to make sure the operator's eyes or face isn't too close. We don't have those very high currents on our network. So yeah, we've stopped actually taking off the guys.
That's interesting to hear, Brad, especially the consideration about the load current and the relationship between that load current and EMF. So I guess it's probably something that you don't think about when you see transmission lines. You think high EMF, but it's actually not the case.
No, that's right.
I had a question around some of the structures that you had in those photos, particularly the aluminium ones. How do you ensure when you're constructing those, that they're earthed, or are they constructed off-site and brought in?
Okay, so that particular aluminium scaffolding that we're using there is a modular, mobile scaffold that we build either in situ or not far from where you're working and wheel it into place. Yeah, it is a requirement, certainly at Powerlink, to have anything metallic like that earth. So we have mobile earths attached to those aluminium scaffolds. The French actually use steel scaffold because it's a little bit heavier. We choose to use aluminium scaffold, and when we have it in situ holding sticks or shunts in place, we actually use counterweights to make sure that we don't have any stability issues holding sticks and things like that.
Okay, fair enough. That's just interesting to see, especially working with what could possibly be isolated lengths of poles people of aluminium as people are building it. But yeah, thanks very much for that.
Obviously, we're very careful about where we build those aluminium scaffolds. So as you imagine, putting those scaffolds together, there's long lengths of aluminium. So obviously, there's set positions where they build it that's a lot safer and wheel it into position when there's tight clearances.
Yeah, that's fair enough and stands to reason. The last question I think we have, unless there's any last-minute ones, but a bit of a higher level, maybe more philosophical, I don't know, sort of question, but do you see this, the live substation work as an option for distribution network operators like Ergon, Energist, and nationally? It's something that the transmission and Powerlink have implemented, obviously, to maintain security, but yeah, do you see any barriers or any issues with distribution network operators implementing this practice?
Yes and no. From a bare hand perspective, there are issues with distribution voltages simply because an operator is, in essence, a certain size, and you just don't have enough clearance distances between phases to put an operator between the phases of a 33 kV busbar or disconnector or something like that. So we at Powerlink, our methods allow us to work down to 66 kV and not below that, and we don't have anything below that. So there's limitations from a bare hand perspective simply due to the size of the operator. However, from a hot stick perspective, there's definitely no reason at all why the approaches that we do with disconnector maintenance using hot sticks couldn't be taken to the distribution side of the business for doing disconnector maintenance, be it routine condition monitoring or fixing problems, shunting out 33 kV disconnectors and so on. I know a lot of the utilities throughout Australia do live line work at that voltage, and some utilities are starting to look at taking their live line approaches and applying them in substations. One of the benefits of the way that we work is that we're not limited by set procedures for a particular type of item where we're looking at our methodology and applying it to each individual case. And there's no reason why you couldn't take that approach to the 33 kV and below switchgear from a hot stick point of view.
Great. Thanks, Brad. We had one more question, which will be the last question we ask today, from Jack, just around PPE, asking what are the requirements for PPE with Powerlink in terms of live substation work.
Okay, so I think the thing there with PPE is with bare hand work. You probably would have seen in a number of those photos that the operators working bare hand wear a conductive suit, which creates a Faraday's cage around the operator. So that's a specialised bit of kit that the guys wear. So they're fully enclosed, their body's fully enclosed except for the face is open. You'll find that on the hood that they wear there's a peak that extends out in front of the face, which enables the face to be open. So yeah, it's a specialised suit that's designed to be a Faraday's cage for that work.
Okay, great. Thanks, Brad. I think we'll wrap up here just because we're nearly at time. I wanted to extend a special thanks to Brad for coming along and giving us time today, and also being a bit of a guinea pig, being the first person we've had